Hello and welcome to this lesson for A-Level OCR Physics, where we're going to be looking at Module 3, Forces of Motion, in the subtopic of 3.4 Materials and on the concept of Hooke's Law. So in today's lesson, we're going to be looking at this idea of Hooke's Law and how to measure the properties of elastic materials. So if we've been successful and we've learnt in today's lesson, we should be able to recall Hooke's Law, calculate values using Hooke's Law, then know the different material properties related to Hooke's Law. So we're going to look at the following part of the OCR A-Level Physics specification, 3.4.1 Springs. So, resultant forces cause an object to change shape, and we call this material deformation. Now there are three different types of material deformation. The first type of deformation is extension. This is when an object increases in size due to a force being placed on it. Now a resultant force which causes an extension is called a tensile force or a tension. Now in this situation we are going to define extension as a positive change. So when tension is applied to an object, it will increase in size. But it's important to note that for this to take place, more than one force must be applied on the object. So for example, if we have two tensile forces applied, it will cause the object to increase in size. Now you'll note from this diagram that tensile forces tend to be balanced outward forces applied. Now the second type of deformation is compression. This is when an object decreases in size due to a force being placed on it. So a resultant force which causes a compression is called a compressive force. Now we define a compression as a negative change, contrasting the extension which is a positive change. So when compression is applied, the object will decrease in size. Now once again, for this to take place, more than one force must be applied to the object. So you'll see in this situation we have two compressive forces applied on this object, and these will cause balanced inward forces. Now the third type of deformation is bending. This is when an object does not change in overall size, but it is distorted. So this means it stays the same size, but it changes shape. Now for this to take place, more than one force must be applied on the object. So it doesn't matter if it's extension, if it is compression, or if it is bending. There are two ways an object can behave if it undergoes material deformation, and that is either elastically or inelastic or plastically. So an object is elastic if the object regains its original shape after the forces deforming it are removed, whilst an object is inelastic or plastic if the object does not return to its original shape if the forces deforming it are removed, so it stays deformed. Now many objects have an elastic region and an inelastic or plastic region depending on the deforming force placed on the object, so this is commonly called being stretched. So at lower forces, objects exhibit elastic behaviour, but at higher forces, objects tend to exhibit inelastic or plastic behaviour. That's because at this point permanent structural changes have occurred to the material at that high deforming force. So to clarify, an object is elastic if the object regains its original shape after the deforming forces acting on it are removed. This is elastic deformation. An object is inelastic or plastic if the object does not return to its original shape if the deforming forces act on it are removed. This is inelastic deformation. And many objects exhibit elastic behaviour at certain deforming forces and exhibit inelastic or plastic behaviour at larger deforming forces. So this can be shown on the following graph, where you can see both your elastic region and your inelastic region. Now, Robert Hooke was a scientist who examined elastic materials by placing a deforming force on them, and he realised the following. The more the deforming force that was put on the material, the more they extended. And with some materials, they extended in a directly proportional relationship. So if the force was doubled, so did the extension. and with a large enough deforming force, the material will snap. So here is an object with a deforming force acting upon it. The deforming force in this case is causing an extension. Now the extension is measured as the difference in length between the length with the deforming force and the length of the object without the deforming force. So extension is the change in length of the material, or delta L. Now we give the original length of the material, therefore, the symbol L. So extension is the length with the deforming force minus the length with no deforming force. So we worked out that the greater the deforming force, the greater the extension of the object. And it's also true for compression if the forces are acting in the opposite directions. So just to clarify, extension is measured as the difference in length between the object with a deforming force and without a deforming force. In fact, extension and deforming force increase at the same rate. They are in direct proportion. As one doubles, the other doubles, which is Hooke's law. Now for a spring, this is the same for either a compressive or tensile force, but it's not the case for all materials. So when Hooke plotted this relationship, he achieved a straight line trend in his graph. Now an object here is in its elastic phase when the graph is in a straight line. The straight line section shows that the force and extension are directly proportional. So when the line of best fit is a straight line through the origin, we know they're directly proportional. So here, if the force extension graph of a material is a straight line, it obeys Hooke's law. The object obeys elastic behavior. Now note, the graph must go through the origin, as when the force is 0, the extension has to be 0. If not, the experimenter has made a mistake as they've measured the length. Now Hooke realised that if a large enough deforming force was placed on the material, force and extension are no longer directly proportional. So this point is called the limit of proportionality. It's sometimes also called the Hooke's law limit. Now Hooke also realised that if a large enough deforming force was placed on the material stopped exhibiting elastic behaviour and started exhibiting inelastic or plastic behaviour, and this was called the elastic limit. Now the elastic limit of a material is the point beyond which the material will become permanently stretched, so will become permanently deformed. Now, we know that when all the force is removed past the elastic limit, the material will no longer be the same shape as it was at the start. Now, for most objects, the elastic limit and the limit of proportionality are not at the same deforming force. In a typical material, the limit of proportionality occurs slightly before the elastic limit. So after the elastic limit, the material acts as an inelastic or a plastic. So that's important to know, because eventually, if the material has enough deforming force placed on it, the object will snap, and this is called the breaking point. Now, the gradient of the force extension graph is called the spring constant or force constant. Now we know that a resultant deforming force should cause an extension, so we should get a line that goes through the origin. As we mentioned before, if it does not, then the experiment has not measured the extension, but they've in fact measured the length. Now the spring constant or force constant is the amount of force needed to extend an object by 1 meter. It's a measure of how stiff the object is. So the stiffer the object, the larger the spring constant. The stiffer the object, the more difficult it is to extend. So we can also call it the stiffness constant. Now this constant can only be taken in the straight line section of the graph. This is because if the gradient is constant, then therefore the spring or force constant is a constant, as the name suggests. Now the spring or force constant can only be measured when the material exhibits elastic behaviour. Now note, the spring or force constant is not the same as the concept of the spring modulus. Now that's given by the symbol lambda, which is lambda equals KL. Now this is only considered in A-level mathematics and not A-level physics. Now we can use Hooke's law to define the force or spring constant and the deformant force. Hooke's law states that the force needed to stretch a spring is directly proportional to the extension of the spring from its natural length up to the limit of proportionality, which leads to the following equation. The deformant force in newtons is equal to the force constant in newtons per metre times by the extension in metres, or if we give it the symbols, F equals K times by delta L. Now this equation only applies up to the limit of proportionality. So this equation is obeyed by wires and solid objects made of most materials. This equation is used for both compression, where delta L is a negative, and extension, where delta L is a positive. Now remember, the greater the value of K, the stiffer the spring. And if a spring is stretched beyond its elastic limit, it doesn't regain its initial length when the force applied to it is removed. Remember, in A-level maths, you meet Hooke's law in the form of F equals lambda delta L over L, where L is the unstretched length of the spring and lambda is the spring modulus. This is not needed for A-level physics. So let's have a look at an example question. A vertical steel spring is fixed at its upper end with an unstretched length of 300 mm. Its length is increased to 385 mm when a 5 Newton weight is attached to the lower end at rest. So calculate the spring constant and the length of the spring when it supports an 8 Newton weight at rest. So to work out the spring constant, we say extension is equal to 385 mm minus 300 mm, 85 mm, which is 0.085 meters. Spring constant is force over extension, so 5 over 0.085, so we get 59 newtons per meter. We can then work out the extension, which is force divided by spring constant. As it's a constant, it's the same for the material throughout, so it's 8 over 59, which is 0.136. So our overall length is the original length plus the extension, so it's 0.436 meters. Now we can calculate the spring constant of a material by measuring the extension of the material and the force exerted on the material. But what would happen if we place the springs in either series or parallel with each other? So we can place the springs in series, and this happens when the springs are attached one after the other. It's like the concept of series in electrical circuits. And we can place the springs in parallel, which is when they're attached side to side with each other. It's like the concept of parallel in electrical circuits. Now we can calculate the overall spring constant when springs are placed in series. Now when springs are placed in series, the tension, which is the force, in each spring is the same and is equal to the weight exerted. So we can say the extension of spring 1 is equal to delta L1, which is F over K1. The extension of spring 2 is delta L2, which is F over K2. So the total extension of both of them, which is extension of 1 plus extension of 2, is F over K1 plus F over K2 is equal to F over K. Now F, the force, is the same in each situation, so it's a common term that can be cancelled out. So we can write it out as 1 over the total spring constant is equal to 1 over K1 plus 1 over K2. So this shows us that the spring constant when springs are placed in series decreases compared to the individual. So for example, if K1 is 30 newtons per meter and K2 is 20 newtons per meter, we would do 1 over 30 plus 1 over 20, which is equal to 5 over 60, so therefore the total K is 60 over 5, which is 12 newtons per meter. So you'll notice straight away that the total spring constant of the two springs is lower than the individual spring constants of each. And this is why it's not common to see springs arranged in a series pattern. Now we can calculate the overall spring constant when springs are placed in parallel. So when a weight is supported by two springs in parallel with each other, the extension, delta L, of each spring is the same. So we know the deformant force on spring 1 is K1 delta L and the deformant force on spring 2 is K2 delta L. Since the weight W is supported by both springs, we can say the weight is equal to F1 plus F2, which is K1 delta L plus K2 delta L, and that equals the total, K delta L. Now the extension, delta L, in all these situations is the same, so we can cancel that out. So we can say that the total spring constant is K1 plus K2, which is the same mathematics as working out electrical resistance in series. So this shows us that the spring constant when springs are placed in parallel increases. So if K1 was 30 newtons per meter, and K2 was 20 newtons per metre, we can say 30 plus 20 is 50 newtons per metre. So straight away, the total spring constant of the two springs is the sum of the individual. It's got greater, and that's why it's common to see springs arranged in a parallel pattern. So to summarise what we've looked at in today's lesson, we've looked at tensile and compressive deformation, extension and compression, Hooke's law, and the force constant K of a spring or wire where F equals Kx. So if we've been successful and we've learnt in today's lesson, we should be able to recall Hooke's law, calculate values using Hooke's law, and know the material properties related to Hooke's law. So thank you very much for watching this lesson in Module 3 of Forces and Motion in OCR A-Level Physics, the subtopic of 3.4, Materials, and in the topic of Hooke's law. Thank you very much and have a lovely day.